Ever wondered about the mathematical realm that allows you to add and scale quantities, not just by magnitude, but also by direction? Welcome to the world of vector spaces, an essential concept in linear algebra and physics that helps us model physical quantities such as forces and velocity. Scene script. Imagine a set full of elements often referred to as vectors. These vectors aren't just elements in a set. They can interact with each other. They can be added together, and they can also be multiplied or scaled by entities called scalars. Scalars typically take the form of real numbers, but can also be complex numbers or even elements of any field. Now, this addition of vectors and scalar multiplication isn't just random. They follow very specific rules or axioms, known as vector axioms. The nature of the scalars defines different types of vector spaces, such as real vector spaces and complex vector spaces. Vector spaces are a generalization of Euclidean vectors, which provide a way to model physical quantities that have a direction as well as a magnitude. They are fundamental for linear algebra, and when combined with matrices, they offer a concise and efficient method for manipulating and studying systems of linear equations. One of the fascinating things about vector spaces is their dimension. The dimension gives us a rough idea of the number of independent directions in the space. What's even more interesting is that if you have two vector spaces over the same field, and they have the same dimension, their properties, dependent solely on the vector space structure, are exactly the same. This phenomenon is technically referred to as the vector spaces being isomorphic. Vector spaces can be finite dimensional or infinite dimensional. Finite dimensional vector spaces naturally occur in geometry and related areas, while infinite dimensional vector spaces pop up in various mathematical contexts. For instance, polynomial rings are countably infinite dimensional vector spaces. It's also worth noting that many vector spaces in mathematics come equipped with additional structures. This is true for algebras, which include field extensions, polynomial rings, associative algebras, and Lie algebras. It's also the case for topological vector spaces, which include function spaces, inner product spaces, normed spaces, Hilbert spaces, and Banach spaces. So to summarize, vector spaces are sets of vectors that can be added together and scaled by scalars. They follow specific axioms, and their properties are largely determined by their dimension. They come in finite and infinite varieties, and often come with additional structures. Understanding vector spaces opens up a new dimension, quite literally, in our understanding of mathematics and physics. It's a concept that doesn't just exist in textbooks, but finds application in various areas of science and technology. So the next time you come across a vector, remember, it's not just a quantity with magnitude and direction. It's part of a grander structure called a vector space.